So, hello everybody. Welcome to MAT 1350, Algebraic Knot Theory. Just very briefly, there is a website, and the URL is written where? On your handout, also at the top over there. I'm not sure I want to go through all the technicalities here. Maybe I will go through some of them tomorrow. I mean, next class. But I do want it on because I will want to go through the handouts that are connected from it. So, the goals of the class are as written here, namely, the first one is a mouthful. So, to construct a polytime computable strong knot invariant with good algebraic properties. And I have to say that this had been my dream for like 15 years. So for about 15 years, hello Jesse, pick up 2 handouts from here. So this had been my dream for like 15 years to construct such a thing, and it's finally achieved. Much harder than it might have seemed. And there is still a lot to do, so I'll have to explain why this was my dream. And now that it is achieved, what can we do with it? But even before that, I will have to go through each of the words here and explain what they mean. So, what is a knot invariant? What do I mean by strong? What do I mean by good algebraic properties? Why do I mean by polytime computable? And why is this a good thing to have? Why are all of these things good things to have? So, at the end, after a lot of work, such a thing exists. And the work ends up being, well, involving quite a lot of math. So, well, when I say hard work, it's a bit maybe misleading. It was a hard work to get there, but the math is beautiful and elegant, and it relates to all sorts of beautiful mathematics that's worth learning regardless of the goal. So even if you throw the goal away, the math that we will be learning, so a little bit about algebras and quantum groups and, well, Hopf algebras, quantum groups, Gaussian, how to manipulate Gaussian expressions, perturbation theory. So this is, in fact, closely related to perturbation theory of quantum field theory. So all of this math is worth learning regardless of the goal. So that's our second goal, to learn this math. And the last goal is, well, this is me. But you know, maybe I'll be able to make it you as well. I tend to believe math only when I can compute it. So to me, math is not just an abstract subject, it immediately becomes computation. And people tend to look down at computation because it's the thing that's done by technicians. But that's a wrong perspective. I mean, the math that we will end up computing is very high level, very abstract, very pure, but yet you can implement it and run it on a computer and get results. And it will be lovely to see how sometimes extremely abstract things can be made into 10 lines of code that runs and produces output that you would have never been able to produce by hand. So that's the third goal, and it's useful beyond this class, and in fact beyond mathematics. It's a good thing to know how to implement your ideas, how to turn them into computer programs. Good. Any questions, any comments right now? Okay. So let's go through explaining, these words in a certain order. I think the order will be not invariant, then strong, then good algebraic properties, and then polytime computable. And I'm only sketching, of course, so explaining everything will take a whole semester, but I want to go through a sketch today so that we basically get oriented, okay? And so everything today will be extremely sketchy, but yet you will see how math enters, how real math enters into this. Okay. So what's a not invariant? We start with what's a not, okay? So, and this is kind of funny, but every time I teach a class in net theory, I make the same mistake, which is I forget to bring a notable object. And then I discover that I have one on my belly. So what's a not? A not is a closed loop in space, considered modulo motions where it is not allowed to self-intersect. I can turn it into a formal definition, but this is an introductory class. I won't. Okay, I will not. So think along the lines of smooth curves in R3 modulo homotopies of such, smooth injective, smooth simple curves in R3 modulo homotopies, whatever, something along. But the intuition is, the words might be, the technicality might be there, but the intuition is clear. So this is a not. It's called the a-not. It's shown here in the center. There are other knots in the world. For example, this one here, assuming I close it, is the so-called trefoil knot. In fact, there are two trefoil knots. There is a left-handed trefoil knot and a right-handed trefoil knot. So there is this one, and the other one I do so rarely that I hope I will get it right. And there is this one. Are they mirror images? I hope. No, I've done the same thing. Sorry, I said it's, again, I do it so rarely that I nearly never get it right. Anyway, here's the other trefoil knot. And then there is the a-knot. And the question is, are they the same or are they not the same? Or I don't know if this is the question, this is a question. Okay? And you may think that the answer is obvious. I mean, they're obviously not the same. I mean, you look at it, but maybe you can deform one to the other. So you may think it's obvious that you cannot untie this. Okay? But maybe you're wrong. So for example, there are three pictures here, and in fact, two of them are the a-knot. Can you tell which two? It's a bit hard. Okay? I think it's this one and that one. Okay? But what this means, so basically, if one can take this one and deform it to be that one, then where's the guarantee that you cannot start from the a-knot, deform it to that, by doing a very, very complicated thing, perhaps. And then, in fact, maybe deform it to something 100 times more complicated than that. So, for example, I think at the bottom, I'm showing another, and it's also, you also have printed copies, right? So, so this is actually yet another version of the unknown. So if you could start from a round circle and deform it to that, where's the guarantee that you cannot go on from that and kind of simplify it in a different way, and the simplification will lead to the trefoil knot? So where's the guarantee that these are really different? Maybe they are equal. Okay? And likewise, the example in the middle, so this is the famous Perko pair. So in a famous tabulation of knots, I'm forgetting the exact history, and every time I say it wrong, and then later I get an email from Perko that I messed up. So maybe I will not say it, but for many years there was a tabulation of knots, and the tabulation included these two, which for a long time were considered distinct because nobody bothered to look hard enough and see that they are actually the same. Because if you look not hard enough, they don't look the same. And then came Perko in the early 70s and realized that they are the same. And this emphasizes that one has to prove that they're different. Okay? So, maybe one more word about knots before switching to talk about knot invariants, is that the interest in knots does not end with showing that they are equal or that they're different. So, or in fact, these are not just curious objects. So in fact, they are the key, or they are one of the keys to studying three-dimensional topology in general, and also four-dimensional. So basically, if you want to construct a three-dimensional manifold or a four-dimensional manifold, often the procedure involves so-called surgery. So you look at a standard three-dimensional manifold, such as R3 or S3, the space in which we live. You put a knot inside it, you remove the knot, so you've removed a solid torus, you remove a neighborhood of the knot, so you've removed a solid torus from the space, and then you glue it back in a different way. And that produces a new three manifold or a new four manifold, depending on what exactly you do. And that's often a key to understanding three and four-dimensional topology. So, you know, it might look that I'm talking about tying shoelaces, but I'm also talking about three-dimensional topology in a much more general way. Okay, anyway, so back to our question, how do I tell that these three things are different? So the answer is I need to construct knot invariants. So what's a knot invariant? Well, a knot invariant, so I mean, I will define it, but it's a loose definition. It's not a formal definition. It's what we mean when we say this, but it's not the same as defining a vector space, which is a very strict definition. So it's a computable quantity, quantity. So what do I mean by a quantity? I mean something that happens in ordinary mathematics. Okay? So again, I'm loose, okay? So meaning an integer, or a polynomial, or a Boolean value, true or false, or a matrix, or a matrix of polynomials, or something that happens in ordinary mathematics and where you can tell, and in which you can tell things apart very easily. So integers have a, for knots it's hard to tell them apart. It's hard to tell if two are the same or not. But integers have the property that, well, it's very easy to detect if they're the same or not. Like 3 is not equal to 7. We kind of all accept this. Okay? So, so it's a computable quantity which is associated, or which can be computed from any, so associated to any so-called knot diagram. So what's a knot diagram? A knot diagram is a projection of the knot to the plane. So in fact, all of the pictures I've shown you here are not diagrams. They're not knots. The knots are equivalence classes of knot diagrams, equivalence modulo deformations. So computable quantity associated to knot diagrams, and which does not change, which does not change when you deform the diagram. And by deform, I mean exactly the thing that I've meant all along. So you deform the diagram, the projection gets deformed. Sorry, you deform the knot, the projection gets deformed, and I want an invariant are quantities that do not change when you deform when you look at the movie of deformations of the diagram that corresponds to deformations of the knot. I could make it more precise, and I will, but this is the first class. Okay? So what good is a knot invariant? So suppose you had a knot invariant. I don't know, in fact, why don't we use one that actually exists? So there is a knot invariant called V2. I don't know why. Okay? And it's a function on the space of knot diagrams with values in the integers. And it has the property that V2 of that is equal to 1, V2 of that is equal to 0, and V2 of that is equal to -1. This proves that the three things are distinct. Okay? Because if you could deform this picture and get to that one, since the invariant is invariant, namely does not change, you would have that V2 of the first picture is equal to V2 of the second picture, but since they're different, you know that the pictures are different. So that's why we care about knot invariants. Why do we care about strong knot invariants? So what does strong mean? Okay? So, well, you know, it turns out that not only these examples exist. In fact, there are many more. So, there is a whole zoo of knots. And here are the first, I don't know how many, 100 or so. And in fact, actually, some of the later pictures are pictures of so-called links. So these are knots that have two components. So the definition is this, or the loose definition is the same. The precise definition was not given. And what it really means is that things that can be made out of two belts instead of just one. Okay? Or three in some cases. So there is a whole zoo of knots. And you'd have to be extremely lucky if you wanted an integer invariant to separate them. if you wanted the integer value associated with each of those little pictures to be different, you'd have to be extremely lucky, and typically you aren't. So a strong not invariant usually takes values in something a bit more sophisticated, polynomials or matrices or something bigger, which makes it have a higher chance of being injective. And then the word strong means good at separating. And of course, strong is relative. I mean, some are stronger than the other. So basically, attains many values. So for example, V2 would fail miserably at separating all of those, but the Jones polynomial, which we will study on Monday, separates them. If I remember right, maybe with one failure. I think it actually separates them. So, yes, I think it's kind of obvious why we want strong invariance. So I'll move on. What do I mean by good algebraic properties? So that's a tough one to explain. So you know, when we're interested in more than just separating knots. So some knots have properties and some other knots don't have properties, those properties. You know, if you want an analogy, you know, some integers are prime and some other integers are not prime. Likewise, there are properties, knots are divided into classes. Some knots are prime, some other knots are not prime. In fact, the same word applies. There are other properties. So for the integers, some integers are the sum of two squares. So 29 is equal to 5 squared plus 2 squared. And some other integers are not sums of two squares. I think 30 is not a sum of two squares. So 30 is not. So likewise, there are other properties that separate integers. And similarly, there are properties that separate knots. Let me give you an example. Does the knot have a ciphered surface? So, does a knot have a ciphered surface? What's a ciphered surface? So, a ciphered surface is an orientable embedded surface in R3 whose boundary, so in particular it's a surface with boundary, whose boundary is the knot. So let me give you a few examples. So example number one, so let's start, okay, you know what, no. Example number 0 is the A-knot. Is this the boundary of a surface? Of course it's the boundary of a surface. It's the boundary of a disk. Okay? But now let's do something more complicated. So the trefoil knot, is it the boundary of a two-dimensional surface with boundary orientable? So let's do guess number 1, okay? So guess number 1, so basically take a band of paper, twist it 3 times and glue its ends. This is the picture you get. So here is the band. Now it gets twisted and it continues this way after the twist, and then it gets twisted again, it continues again and gets glued to itself. So it looks like the trefoil is the boundary of a 2D surface. But I forgot one word, and the word I forgot is orientable. This is not an orientable surface. So this is not orientable. So if the trefoil is the boundary of a surface, I am yet to show it. Okay? So this is a bad example. Is it okay if I write here? Okay, so let's do a little bit more on the trefoil. Here is another way to present the trefoil as the boundary of a surface. So the surface will be essentially the triangle inside. Of course, it's not a triangle. When I say triangle, I mean loosely speaking. It's a shape in the plane with 3 corners. Okay? It will be the triangle outside, so basically the complementary part of the plane. And these 2 triangles are connected to each other via 3 twisted bands. So you put a twisted band here, like you put a band of paper and you twist it and you connect it to the external triangle on one side and the internal triangle on the other side. So basically this. Likewise another one here, likewise another one here. Now, this is again a surface whose boundary of the knot, and this is an orientable surface this time. Because you see, I could color the sides of the surface black and white, and then if here the side that's showing is black, then after the twist, the side that will be showing on the outside will be white, and that's consistent. That's what happens in all 3 twists. So it's all so everything is consistently oriented, okay, or consistently made to have 2 sides. Okay. So the trefoil is the boundary of a knot. Sorry, the boundary of a surface. Do people here know the classifications of surfaces? So there is a classical theorem which I don't think we will prove in this class, but one should know, which says that if you are looking at orientable, connected. So you see, I didn't say the word connected when I defined a Seifert surface because it's kind of pointless. If you have a disconnected surface, you can drop the components that do not touch the knot. So having a disconnected surface or a connected surface is the same for knots. But the classification theorem is about oriented, connected, 2-dimensional surfaces with 1 boundary component. So the theorem says that all such surfaces are in the following list. So basically the sphere, but you see I wanted it to have 1 boundary component, so you remove a disk. So the sphere with a disk removed. The sphere with a disk removed is really just a disk in itself, and we already saw it over here as the thing whose boundary is the unknown. Then there is the so-called genus 1 surface, which is a torus with a disk removed. Then there is the genus 2 surface, which is a thing with 2 holes and a disk removed, and then a thing with 3 holes and a disk removed, and so on. So the number of holes is called the genus. Here G is 1, here G is equal to 2, here G is equal to 3, and here G is equal to 0. Why did I mention it? Because I wanted to ask you a riddle. I mean, this is a bit of an aside. It's not a part of the main thread of today, but I wanted to ask you a riddle. You see, that's a theorem over there. Theorems are always true. But here is a surface which is orientable, connected, has 1 boundary component, so it must fall under this theorem. And then the question is, so which surface is it? So again, this is not a part of the thread. It's a riddle for you. Figure out which surface is this. In other words, what is G? Okay? Phew. Why did I tell you all this? Okay, it turns out that all knots have ciphered surfaces, but not all knots have ciphered surfaces of the same genus. So some knots can be presented as the boundary of a genus 1 surface, and some cannot. Likewise for 2, and so on. So you're not only interested in separating knots, you also want to know how they interact with surfaces. And again, this has applications in 3-dimensional topology in general. So you may want to know whether a knot is the boundary of a genus 2 surface or not. Okay? Next comes the next theorem. So, theorem so a knot is the boundary of a genus 2 surface if and only if it comes from the following procedure. So what's the procedure? You start from a caravan of 2 double hump camels. So here is 1 double hump camel. Sorry, here is 1 double hump camel, and here is the other, and that's a caravan of 2 of them. Then, by the way, this isn't a circle, this is a graph. Topologically, right, this has vertices. It's not a circle. But, well, it's still nearly a 1-dimensional object. Then you knot it. So, well, I haven't defined knotted graphs, but you can imagine that you can define them. Well, I haven't defined knotted circles either. Okay? So what does it mean to knot it? It means, for example, God, this is way above my normal drawing skills, so I'll draw, I guess, I don't know, you can pull a piece of this strand and pull out a piece of that strand and let them knot with each other. Okay? and then you thicken it. What does thicken means? It means, well, you know, draw with the wide side of the chalk instead of with the sharp side of the chalk. Okay? So let's try to do it. You get this at the bottom. You get this picture. Okay, you got this picture. But what's this picture? This picture is now a two-dimensional surface with boundary, right? The surface is, well, you can see, it's a thick kind of, these are bands, okay? So it's a two-dimensional surface with boundary. What's the boundary? The boundary is, well, maybe I'll mark it in a different color. So the boundary is this funny thing. And you are welcome to check that the boundary, God, it's a complicated one. You are welcome to check that the boundary has a single component, so the boundary is a knot. So this red knot is a knot which is presented as the boundary of a surface. You can check that this surface has genus 2, and every genus 2 knot is obtained by this procedure. You don't have to believe this theorem. Later we will prove it, but you know, this is class number 1. So what was the key point? The key point, somehow in this construction, I mean, the construction had several parts, but somehow the big part of it, the most interesting part of it, was this passage from having a single strand to having 2 parallel strands. Okay? So what is good algebraic properties? So good algebraic properties would mean good behavior under not operations. So not operations. And what are not operations? Well, we will have to go through operations later, but the main one that's interesting for the example at hand is the operation where you take one strand and you replace it with 2. In fact, if you look at it, they tend to have opposite orientation, so maybe I would write it this way. So that's an example of a not operation. Now, what does a good behavior mean? Well, so operations form a structure, right? In group, you have multiplication, and they form, you know, it's associative, and it, whatever, I don't remember what's the definition for it. Okay, something. So these operations or nots also form a structure. And I will say that an invariant has good algebraic properties if it's a homomorphism. If it's a homomorphism, then sometimes you can read properties of objects from the... Basically, you can speak about objects that are defined using these operations. You know, very loosely, it's similar to, well, you know what, forget it. Maybe I should move on. Okay. I only have 10 minutes, and I wish I had a little bit more. Okay, I'll very quickly tell you what is polytime computable, and then start with the actual content. So, well, the nodes we care about turn out to be big. So, there are conjectures and open problems about, you know, whether all nodes have a surface whose boundary is this node with such and such properties. Okay? And such conjectures, well, the counterexamples tend to be big. So nodes with 50 crossings, not tiny ones like that, but more like the complicated anode that I was showing before. So you want to be able to compute your invariance relatively quickly, and mathematicians tend to ignore this completely. So mathematicians often, you know, write a formula and they don't care how long it takes to compute. But formulas that involve 2 to the n computations are not going to be computable for nodes with 50 crossings. Okay, so I want things that are computable in polynomial time in the input. Otherwise, I will not be able to say anything about these conjectures. Okay. That's the end of what I have to say about my wishful thinking, right? I want such an invariant. Now, how do I mean, of course, I have to say a lot more to make it concrete, but now how do we achieve this? So we achieve this using the so-called, or what I will call, the Young-Baxter technique. So this, it's old. This is not new. So this is some stuff from the 80s. Okay? So what's the Young-Baxter technique? So it's a technique for constructing not invariants. So you pick an algebra. So your input, so the input is an algebra A. Do we all know what's an algebra? So algebra is a vector space that also has a multiplication operation. So basically it's a vector space A along with a multiplication map from A tensor A into A, which satisfies some conditions. It's associative, I don't know, it has a unit maybe, I don't know. So the input is an algebra A and an element of A tensor A, so an element often called R, which lives in A tensor A. What does it mean that it lives in A tensor A? It means that you can write it in the form sum of AI tensor BI, where AI and BI are elements of the algebra. Now, how do you construct an invariant out of this? You do the following. You say, well, basically you say you put a copy of R on each crossing. So every time you see a crossing, you put on it a copy of R. What does it mean? It means that, well, the crossing has 2 strands involved, an upper strand and a lower strand, and you put the A's on the upper strand and the B's on the lower strands. So you put AI here, BI here. And you do it for each of the crossings. So you'll have AI here, BI's here, And I think I want to separate the different copies, so I use different indices. So you have AJ here, BJ here, and AK here, BK here. And now you turn this into a product in the algebra by starting somewhere along the knot and then multiplying. So you go along the knot, you see a BI, then you see AJ, then you see BK, then you see AI, then you see BJ, then you see AK, and that's a product in the algebra. And then you sum, so really I wasn't putting AI and BJ, and AI and AJ, I was putting R. R is a sum. So I sum over I, J, and K, this product that I get, and the result is an element of the algebra. That is a way of assigning a quantity to a diagram. If R satisfies some good conditions, namely if it satisfies the so-called Young-Baxter equation, so if R satisfies the Young-Baxter equation, you get an invariant. You get an invariant. Namely, you get something that does not change if you deform the knot. I wish I had time to tell you more. This is the beginning of a lovely story, but let me say a few things. Okay, so first of all, but it has to be very quick. First of all, how do you find such an algebra? Second, well, what about the thing that I raised, the good behavior under these operations? So it turns out that the good behavior under this operation means that the algebra needs to be a so-called Hopf algebra. So what are Hopf algebras? How do you find Hopf algebras? How do you find Hopf algebras inside which there are R elements which satisfy the Young-Baxter equations? So this is, well, you get them from quantum groups, but we will have to talk about that. Okay? Then, but then all of this is a complete failure. Okay? So all of this is a complete failure because you see, if I put a copy of R on each crossing, then I have as many summation variables as there are crossings. If each summation variables runs from 1 to 7, in fact, in most situations, in most examples, the summation will be, in fact, infinite. But even if it was finite, even if the summation was from 1 to 7, if you have one summation from 1 to 7 per crossing, then the total number of summands is 7 to the number of crossings, which is exponential. So you lose. So yes, this defines an invariant, but how do you compute it? So it turns out that you compute it by, well, no, I don't have time to really explain. But that's the content of the course. So the computation will involve replacing expressions in the algebra tensor itself by some sort of perturbed Gaussian formulas for these expressions. And the space of such formulas turns out to be much smaller and so manageable. But then we will have to learn how to manage perturbed Gaussians, and that's content from quantum field theory, or related to quantum field theory. Well, content that evolved from quantum field theory. And I'm already 9 seconds late, so I'll stop. Next time I'll construct the first strong not invariant, the easiest strong not invariant, the Jones polynomial. Okay. You can turn off the video. Sorry.